acid-base direction. Similar to Le Chatelier's principle, we're going to look at which direction it shifts, right, towards the left or towards the right. And we're also going to take a small introduction look at Ka. So we've had a lot of experience so far with our videos together for K, right, for, subheadings of equilibrium constant, whether that was Kc or whether that was Kp, and now we're going to be seeing a little bit of Ka. So it's just the equilibrium constant, okay, specifically for the acid dissociation. What does that mean? It's pretty much the relative strength of the acid. So the bigger number, this one would be, the stronger the acid it is. Similar to a base, Kb, it's going to be the relative strength of the base. The greater the Kb value, the stronger the base. Okay, so I'm going to have a look. I'm going to have a look at Ka as well. Now, previously, in the previous video, we looked at an example where there was not a lot of dissociation into its constituent cations and anions. For example, the H3O plus and the OH minus, because this here would like to stay as the water. Only a very small fraction of it would dissociate into these. So if I were to give you a chart like this, you can see how this here is our H2O. Very, very large number in terms of our concentration. But you can see its constituents, cations and anions, or here this will be the cation, this will be the anion. You see how they are an extremely low number, right? 1 times 10 to the negative 7. This is because only a small fraction of this will ionize into these. Only a small fraction will ionize, okay? Now, small fraction of the H2O, okay, be specific for the H2O, only a small fraction of this will ionize. Now, what if we have a strong acid? So let's assume this HA here is our strong acid. So it's not just going to be a lone H2O just on its own. We're going to have an acid here. It's going to dissociate, sorry, it's going to break up and mix with this H2O and create these respective cations and anions. Okay, so what if we have this strong acid over here? Well, this here is our strong acid. Let's label that over here. Now, obviously, H2O is going to remain constant. Nothing's going to happen to it. But how about the actual HA? Okay, well, as soon as the HA goes in, look how small the value is. It's very, very small. But what can we see over here with our H3O plus and our OH minus? You're going to have a value much greater than the previous example of 1 times 10 to the negative 7. Let's say now it's like 1 times 10 to the negative 2, okay, for both of these. So it increased a lot. So what is this trying to mean? Well, if we have a strong acid over here, we could conclude that it will break up 100%. Okay, this strong acid, it will break up 100% into its anions and cations. And I know we got to use this term lightly over here, 100%, because we still have this value over here. Okay, it's not obviously 100% dissociated, it's not all gone, okay? But here we could actually just say that it's negligible, okay? It's a negligible, I'll write this here, negligible, okay, acid floating around. Okay, so we can just deem it as negligible. So we can still list this definition as suited, as accurate. Now, if we compare this strong acid example that we had versus this kind of graph, we can exemplify here and see that it's very similar to the previous example before this one. Okay, so this here was the strong acid. I'm talking about the example before that. You can back up the video a little bit. When we looked at H2O, it has a similar feat over here, okay? Rather than just looking at H2O right now, though, we are adding another acid over here, HA, okay? But this one, again, is going to be in respect to a weak acid. This being mixed with the water dissociating. Look, we have 4 times 10 to the negative 3. Very, very small number. it's not very large, okay? But because this is a weak acid, not a lot of ionization is gonna occur, okay? So in this one over here, you see how it's very, very small. It's all the way down here. This one, it's not, okay? It's not down here, okay? Not like this one. It's more so up here, okay? It's quite large. So because it's larger up here, not a lot of it is gonna dissociate into its constituent cations and anions, okay? So obviously over here, you notice how they have increased quite a lot, right? This one here dissociated into these, and as you can see, they are a quite large of a number, right? 1 times 10 to the negative 2 and 1 times 10 to the negative 2, quite large, okay? However, here, a lot lower, okay? Only times 10 to the negative 5, times 10 to the negative 5, they're a lot smaller on this graph, okay? So in summary, in short over here, if you have an acid like this, okay, a strong acid, a lot of it is going to be negligible. It's going to pretty much break up 100%. As you can see here, almost all of it is pretty much gone. And as you can see, it rose a lot in terms of what it is yielding, right? The H3O plus and the OH minus, okay, it's quite high up here. As opposed to this one over here, as you can see, 4 times 10 to the negative 3, not a lot of it dissociated, right? Not a lot of it went downwards. It's kind of staying at a relatively large number of 4 times 10 to the negative 3, which means not a lot of this is going to dissociate into these products, okay? And as you can see, it's staying quite low on this graph of times 10 to the negative 5, as opposed to a larger value of like times 10 to the negative 2, as you can see in contrast over there. Does this mean when we overall look at a summary of a weak acid? Well, we can see this HA over here. We got to summarize here that some of this acid is still in the solution. Okay, or simply put, if you want to make it a lot easier, only a small amount ionized. Now, we're going to start looking at Ka, this value over here, because when we look at this Ka value, we're going to start understanding how a reaction proceeds, okay? When you have, like I said, a Ka value that is larger, if the Ka value is larger, the reaction will always proceed from a stronger to a weaker acid. I'll write this over here. Reaction proceeds from stronger to weaker acid. Let's have a look at a few questions. Before I give you the first question, let's define Ka in here in writing, okay? Ka, it's the relative strength of acids. So the larger it is, the stronger the acid. That should be quite simple. Let's have a look at an example here. Let's have our acid mixed with our water here so that they dissociate and it becomes dissolved in the water, and as you can see, hydronium got released, and then there's a certain amount of acid that is still left over. So if we were to do our Kc, let's say we're dealing with molarity, okay, not partial pressure, let's say we're dealing with molarity here, and it's going to equal our equilibrium constant expression. Let's write it out. So obviously our products are always going to be on the top, and our reactants are always going to be on the bottom. Of course, out of these, only H2O here is going to be the liquid one, right? So it's going to be a constant concentration, okay? So we're going to have to get rid of this one. It's the only one that can't be part of our equilibrium constant expression, so we got to get rid of it. If we do it on the right side, you got to do it on the left side as well. You should be comfortable with this at this point. If you don't have any idea what I'm doing right now, please look at the previous video. The link is in the description about the equilibrium constant expression. So now we're just going to be changing this into our Ka because this has to be integrated within the equilibrium constant. So now again we're dealing with just the acid here, so we're going to be looking at just Ka. And this is what we're going to be dealing with. Now, this is very similar to our ICE table. In our ICE table, at the end of it, we had to create our reactants and our products embedded within that table and giving it certain initial concentration values, as well as any changes that went on and what happened at equilibrium. It's very similar to what we're looking at over here. This is going to be our products and in the ICE table, and this is going to be our reactant in the ICE table. Our H2O is not going to be there because it's pretty much ruled out and it's reintegrated into our KC, so we can just leave it blank. You'll have an understanding of this better once we start doing some practice problems, okay? But pretty much as long as you follow this equilibrium constant expression and you fill in the values of each one appropriately, it's going to be a simple division, and then you honestly easily get your Ka. That's it. So whatever Ka value that you get, if you get a Ka value that is less than 10 to the negative 3, it's going to be weak. If you have a Ka value that is greater than 1, it is going to be strong. If you have a Ka value that is between 1 to 10 to the negative 3, this is going to be considered a moderate strength of acid. Now, there is one more formula that I want you to look at. It's the percent dissociation formula. Why is this going to be important? Because for weak acids, that only partially ionize, we got to look at this kind of formula. Okay, the percent dissociation is going to equal whatever amount of concentration of the acid that we had that actually dissociated over how much was supposed to be initially dissociated to completion. So you could also just put initially. Okay, you divide this, multiply by 100%, that is going to be your answer. Let's have a look at some practice questions now. Looking at this question over here, we have to predict the direction for the following reactions. And I did mention already that the reaction proceeds from stronger to the weaker acids, okay, or stronger bases to the weaker bases. Well, let's have a look at this one and this one. This here is obviously going to be the acid because, as you can see, it has lost its H because there's no longer an H over here. This means that whatever has been remained or formed after that H, that hydrogen, that proton got removed, that's always going to be our conjugate base. If you're confused why, see the previous video about conjugate acids and conjugate bases, link is in the description, and this would be the acid that got affected. That means this would here have to be the base, and it makes sense because, as you can see, there's no H here, we've added that H there, so this would be our conjugate acid. Then we got to see which one is stronger. So that's why we have this little chart over here. Okay, this is the relative increase or decrease strength of its conjugate acid base pairs. So if we were to look at this acid, so this acid over here, and let's have a look at that acid over there. Where is HF? It's right over here. Where is HSO4? It's up here. As you can see, this HSO4 here is higher in strength. So that's why I'm just going to be putting down here that this is going to be stronger. It's higher up on the list, right, than the HF. So this would be weaker. Okay, let's double check that with our bases. We have our SO4 2- and our F-. Where is it? SO4 2- up here, F- down here. So of course our F- here is stronger because it's lower on this chart. Okay, again, you can see here increase of base of strength is going to go downwards. So of course F- is going to be stronger. So this here is also stronger. This here is going to be weaker. So it's pretty easy to tell that this side is going to be stronger. Of course, like Le Chatelier principle, if there is a greater amount here, how do we alleviate that stress? We got to go in the opposite direction. So same thing here, okay? But stronger is going to go towards the weak side, okay? So therefore, the answer is to the left. With this question, similar. Let's have a look at this one and this one. It's pretty easy to tell that this was the acid because the H got removed over here. So whatever was left was always going to be our conjugate base. So this is the conjugate base. Okay, this here would then have to be our base, and obviously this here would have to be our con acid. Okay, as you can see here in this chart, we have a problem because a lot of these compounds that we see here in the question are not listed. So how are we going to do this? I want you to pause the video, give it a try yourself, okay, and then I'll be doing this with you together, so just hang along. So hopefully you give it a try on your own and try to figure it out. As you can see, our NH3 here is very, very low on this chart, which means it's not going to be acidic at all. It's actually going to be quite basic. So can we assume that this one here is going to be very, very strong? Can we actually write this here? Let's just write it here for now and preface it for it before we have a double check on other ones. So we're going to say that this is going to be a lot stronger than, let's say, this base. Okay, so let's say this is going to be weaker. Let's double check with our acid here. Well, our acid, it's not listed here, but very similar to HBr, this is hydrobromic acid, or HCl, hydrochloric acid. This is H2S, hydrosulfuric acid. They're all kind of in the same categorical group, okay? So it's likely going to be somewhere up here. As you can see, it is going to be extremely strong acid, okay? So we're going to assume that here it's also going to be very, very strong. Okay, compared to its counterpart acid, our conjugate acid over here, which would be our NH4 plus, very, very small. We have that on our chart. It's extremely low on the chart. Okay, so I think it's very, very safe to say that this is going to be here weaker. So we've confirmed it to be true. Stronger here, therefore it's going to go towards the right. Now let's have a look at this question over here. Same thing, we got to figure out if it's going to go left or to the right, right towards the reactants or the product. So we have sodium hydrogen sulfite. And it's going to add with water. It's going to dissolve in the water. Let's forget about the states for now, okay, like these ones, because I just want to show you something. What are we going to create for the product? We don't actually need to continue, because what does it say immediately after? The sodium hydrogen sulphite, okay, that's this one over here, dissociates completely into the sodium ions and hydrogen sulfide ions. Okay, so does that mean that this one and this one over here are sodium and hydrogen sulfide ions? Should we start adding them in our product? Well, we don't actually need to, because what does it say? What happens to this hydrogen sulfide ions in water? Okay, so whatever happened to this hydrogen sulfide ion, instead of adding it here, we should create another reaction when it mixes with water. Okay, so again, hydrogen sulfite would just be this one. Okay, this will be hydrogen sulfide. It is an ion, so we'll have that over there. Okay, again, we have one H over here because, of course, SO3 or SO4 has a 2- charge. That one charge, okay, got moved down here, so it's going to be H, SO3. That's why there's only a -1 here instead of a -2. But we don't care about what's happening here as a product. We want to make this a reactant now, because it literally says in the question, what happens to this hydrogen sulfide in water? Okay, so we're going to now add it with water as well. So we're going to take this, create another line over here, and add it specifically with the water. Okay, so now what's going to happen? Well, we know that this is a strong acid. Why is this a strong acid? Because it literally says that it dissociates completely. Okay, so that means this thing here, does it turn into an OH, or does it turn into an hydronium, or H3O? Well, of course it has to be H3O. If this is going to turn into H3O plus, this means that an H got added towards it. Okay, and if an H got added towards it, a proton got added towards it. Remember, when it receives a proton, okay, it's going to be an acceptance of that proton, which is the definition of a base. So if this here is our base, then what does this have to be? This has to be an acid, right? Remember, if one is a base, it has to be an acid. If another one's an acid, the other one has to be a base. So if this is going to be our acid, it's going to release that H. Okay, so if it releases that H, now what are we going to have? We're just going to have SO3. Okay, so this H got removed. Okay, then rather than the charge to be a -1, it'll just be a 2-. Okay, so here is going to be, again, this one here, what got added, okay, whatever got formed after that hydrogen got added onto it is going to be our conjugate acid. Okay, if you're confused as to why, see the previous video, link is in the description for conjugate acids and conjugate bases. Now for this acid, what got removed and what is formed, okay, after that H plus got removed is always going to be a conjugate base. We're going to write it as such. Now we got to figure out which one is going to be stronger, which one is going to be weaker. So if you look at that chart, which one is going to be stronger, the HSO3 or the H3O plus? Well, where is HSO3? Well, we don't have it, but we have something similar. We have over here our HSO4. Okay, so we have that over here. Let's have that as a benchmark. How about the H3O plus? Oh, look at that. It's right on top of it. As you can see, H3O is higher. Okay, so the H3O, our hydronium, is going to be a stronger acid. So let's write that down. So this here, again, is going to be a stronger acid. Okay, this here is going to be weaker. Let's confirm with our SO3 2- and our H2O. What's going to happen? As you can see, we have our H2O. We don't have our SO3, but at least we have an SO4, which is going to be quite similar. And as you can see, our SO3 2-, or in this case, the SO4 2-, is stronger. Okay, it is a stronger base compared to this H2O. Okay, so SO3 2- is going to be strong. Okay, so we're just going to be putting here stronger. Obviously, this is going to be weaker then. They all check out. So obviously, the answer is going to be towards the left. All right, let's have a look at this question over here. We've been given our concentration of 0.52 moles per liter. Okay, and this is for our citric acid. Has a pH of what? 1.72. And we know in our formula that pH is equal to the negative log of whatever concentration is going to be for our hydrogen ion. Now, we're just going to plug this into here. If we want to find out our specific concentration, let's bring this up here, we got to obviously divide this by negative log. If we're going to do it on the right side, we got to do it on the left side over here as well. So let's give it a shot. What do you get? You end up getting an anti-log, so that would be 10 to the power of 1.72, but again, it's anti, there's a negative over there, so we're going to be putting a negative pH value up here, okay, which would be our 1.72, so it'll be 1.72. What would this value be? You end up getting 0.01905 moles per liter. Okay, so this here is going to be the total amount of the H plus that got dissociated. Now, we got to still figure out our acid dissociation constant, our first part of this question. Well, we have to figure out how we're going to be doing our Ka. Normally, we have our products on the top and our reactants on the bottom, but we don't have a balanced chemical equation over here. So in this case, whenever you're in doubt, please use an ice table. We have an ice table over here. Let's draw it out. Got to be putting our reactants always first. So our first reactant is going to be, let's say, our HA. Then we have our H2O. That's always going to be constant, so we're just going to leave that blank. We don't need that. And then how about our products? We're always going to be given what? An acid as well as the hydronium ion concentration. If you want to be a little bit more specific with our ice table up there, instead of just saying A to the negative and then HA, you could actually kind of change it where we have our HA going to be our citric acid, which is obviously our reactant that we're dealing with. So we could put C6H8O7. Obviously this here is going to be our H2O, that's not going to change. But here for our products, remember this here has gotten turned into C6. It's not going to be H8, it's actually going to be H7 because we lost that proton. Okay, it is an acid. Remember, this here is an acid. Okay, it's HA. HA is an acid. Okay, so if it released that hydrogen, it has to be an H7 over here. Okay, so our O7 stays the same, and then of course it's going to be negative because obviously we lost that hydrogen. Okay, we're a little bit more negative now, hence why we have a negative charge. Okay, it is an anion. So now what we're going to have in terms of our production is obviously going to be our H plus or H3O plus. Okay, that got released. So let's finish off with our ice table. How much do we have in the beginning? Well, we had a concentration when it got prepared as 0.52. How about here? Well, we don't know what's been produced yet, and we don't know what's been produced here yet either, so we're just going to be putting a 0, like always, for our products. And we don't have a balanced chemical equation, so we're just going to be putting, obviously this got used up, so it has to be a negative, and we have to use at least a variable, so we'll just put negative x. Okay, and then this one here, again, no chemical equation, so we'll just put a positive because these got produced, these were gained, okay, produced, and then of course we'll just put x as our variable here as well. So if you just put this at equilibrium, you just sum them up, you end up just getting x and x in here, and 0.52 minus x over there. So from here, all we need to do is do our Ka, okay, our equilibrium constant expression. Okay, we have our products on the top, and then our reactants on the bottom. Let's do that. So we have product on the top, and then our reactants on the bottom over here. Now, we're just going to fill in the blanks, okay? Well, how much actually got ionized? Well, remember, H plus is the same as the hydronium, okay? It's just the concentration of that ion. So what we're going to do, we're going to be putting this into here. And remember, if this is X and this is X, they're both X. Technically, both of these are going to be the same value of 0.01905, okay? So this value over here, let's finish this off, is going to be 0.01905 multiplied here, okay, with another 0.01905. If you just want to square it, it'll be a lot easier. You can do that too. And then we have 0.52 minus, again, our X is going to be our 0.01905. You do your little calculation, tell me what answer you get. Getting 7.24 times 10 to the negative 4. This here is our Ka value. Now, what percentage of the citric acid molecules actually ionized in the solution? Well, like I said, this here was the value that I got produced, right? That actually got ionized. So again, in our formula for percent dissociation, what did we have on the top? Did we have initial concentration on the top, or did we have what got dissociated on the top? Obviously what got dissociated. So if this is the one that got dissociated, we've got to be putting this one on the top. So we're putting 0.01905. And then what was the initial amount that we had? Well, we obviously just had 0.52 because that's what we prepared in the beginning. Okay, so we'll put 0.52 down here in the bottom. Just divide them, multiply by 100%. What value do you end up getting over here for our answer? In 3.7%. That's the answer. All right, these two questions are the green questions of the day. Please pause the video. Take a minute to try this on your own. Please do it as best as you can, and I'll be giving you the answers shortly. This is the answer to the first question. This is the answer to the second question.